Good morning. So let's continue on with a few more questions from the test review for Calc 2. Vectors, and then at the end, the last question we'll take a look at is coming up with a linear equation in 3 dimensions. Okay, so let's go here. We'll start with this question. Find a unit vector normal to this. So the two parts to this really is the the normal, or the unit, and the normal. Normal means perpendicular. Well, this is an equation of a plane, and notice there is no y direction, or I guess we could say it's 0, right? So you could see that this is going to be basically 3x, 3 in the x direction, the I direction. Hopefully, I'll write this out to get. So the vector 3i plus 5j. No, not j. K. Okay. 3i plus 5k. That's going to be our normal vector. Okay. And it might not be obvious because of all this other stuff, but I'll take you through the steps. So we distribute the 3. We get 3x minus 3. And we distribute the 5 plus 5z plus 15 equals 18. And then notice the two numbers will combine into, let's see, 12, positive 12. So then you'll subtract 12 from both sides. I'll subtract 12 here. And the final thing we end up with is 3x plus 5z is now equal to 6. Okay, but the normal vector from our notes, from what we've done, comes right from here, and it's those coefficients. It's 3 in the I direction plus 5 in the k direction from here. Okay, so that's our normal vector. And so to make it a unit vector, what we need to do is we need to divide it. Let's see, let's call this something. Oh, they call it over here u. It's not quite u yet. It's a vector, certainly. It's a normal vector. But to make it the unit vector, we need to divide by its magnitude. Okay, so to get the magnitude, we use the Pythagorean theorem, so it's going to be 3 squared plus 5 squared equals the magnitude squared. So the square root of 3 squared plus 5 squared is going to give us our magnitude. That's 9 plus 25. That's 34, right? So square root of 34 is not a perfect square, so we'll just leave it as square root of 34. And that's what we need to divide each of these components by. So what is u going to be? Simply 3 divided by square root of 34 I plus 5 square root of 34 k. And let's do the reveal. There we are. Oh, yeah, be careful. A 34. I probably would have caught that if I would have had to re-enter that, but let's see if it'll let me. It is going to let me erase. Maybe I'll go with that. Anyway, guess let's come back to this. So that's a, let's see, I've got to be able to get this fixed. Sorry, you can fast forward through this if you want. This is, this is 34. There we go, 34. We'll leave it at that. Okay, so now we move on to this. Find a non-zero vector perpendicular to these. Now, if we took the dot product, remember, gives us a scalar, so that's not going to work. But when we take a cross product, that's what we end up with, is that vector that we end up with is perpendicular. Okay, so we can just go with V cross W. Okay, that's going to be one of the vectors. Now in this question, you would choose from which one is correct, because there's actually more than one. Right? There's an infinite number. Because you could change the magnitude. You could also move it, but it would be perpendicular, I guess. Anyway, multiply by scalar, all those kind of things. So let's line this up. So what do we get? We get the I, the J, and the K components. 11 minus 9, positive 9. Positive 9 minus 10, and positive 9. Okay, so remember, in getting the cross product, the I component is going to be the cross product of the J and the K components. So it's negative 9. Let's see, where should I put that? Let's go here. Negative 9 times 9 minus 9 times negative 10. I'll put the negative 10 first. This nice thing with the multiplication of scalars, multiplication of numbers, you can do it in either order. So that's going to give us our I component. Our J component is going to come from crossing the I and the K, but remember, we do it, this is the one that the subtraction part is sort of backwards. We do this first, 9 times 9 first, and then we subtract the 11 times 9. And then when we come to the K, it's going to be the cross of the I and the J. And again, we start from the upper left and go down. So this is going to be the first part, and then we subtract the second part. So for this part, it's 11 times negative 10 plus, no, not plus, minus. It's always minus. That's my difficulty is and again, I know a lot of students, myself included, would say it's just a negative, but a negative is a big deal because it puts you on the other side of 0, right? So we subtract now negative 9 times 9. Negative 9 times 9. And that's going to give us our K component. Again, there's little arrows over here, but if you're like me, you just get tired of drawing the little arrows. Okay, so this gives us negative 81 minus, actually plus, negative and negative is going to make it a plus, right? 90. So that's going to give us positive 9. Okay, so that's one vector, I. We'll go ahead and put that there. Here we get 9 times 9 is 81, positive 81. And then negative 9 times 11 gives us a negative 99. So that's 9 plus 9 more, that's 18. That's a negative 18i. Sorry, J. Too many letters, too many. But what I find in mathematics, at least for me, my errors were usually things like that, and then I think I don't really understand, I'm not getting it. Well, it was just I was going too fast and not paying close enough attention. That's one of the things you learn from math, is you learn how to focus You may never have to deal with vectors. I don't know. Depends on what you're doing. If you're engineering, you probably will. But whether or not you do, this is a good learning lesson and learning how to focus on certain things. So 11 times negative 10, that's going to be 121, right? Minus 121. No, I'm thinking that's 11 times 11. This is 110. Yeah. See, my problem is I can't talk and chew gum at the same time. Or walk and, what is it? Walk and chew gum. Hopefully you don't talk and chew gum at the same time. That's kind of, well, I guess, you're supposed to stop chewing. Okay, anyway, negative 110. And then we got a negative, so that's going to make that a positive 81, right? And so there's a subtraction going on, and actually that's not going to be plus anymore. That's going to be a minus. And how much minus is it going to be? Well, that's 20 to 130 less 1, so that's 29. Okay, so there's our vector. It's a choice. They give you the list in the homework. Make sure you choose that one. Again, I just took them out. I think I did. Did I put anything? Yeah, I didn't even put the answer here to check on. So you might get slightly different numbers anyway, but that's what you have to do, is you just kind of, okay, that's the one I want. And we have to give you a choice, because we could come up with the other one. We could multiply this by 2, right? And that would just be, it would still be perpendicular, it'd just be twice larger. You could also multiply it by 0. That's why non-zero vector. Anyway, let's keep moving. Now, these are the ones going to take a little bit of discussion. Let me see. Maybe I should come back here. I want you to get used to using the note sheet we came up, the formula sheet. See, where's our practice first? So I got all that stuff there. Oh, I think I put it up in here. Formulas for first exam. Get used to working with this. Okay, we talk about the cross product. Cross product here are not parallel, then this equals that. Where do we talk about it being, okay, yeah, it talks about it being a unit vector pointing in the direction given by the right-hand rule and parallel. So the geometric definition, remember with the right-hand rule, we're always getting, when we do a cross product, we're getting a vector that's perpendicular either this way or this way. So it's just the direction of it's pointing. That's what the right-hand rule gave us. That's what the explanation gives you. But I didn't remember seeing that directly in the text, but that's the result of doing a cross product. Okay, so now just to kind of review for here, where's our, I think, force is, so work given by a force on a displacement vector F dot D. So the dot product gives us the force. And then over here, we look at the components. So for the component of a vector, of a force vector to be what components, the x and y, so the parallel and the perpendicular components to a vector, what we need to do is we need to do a cross product with a unit vector in that direction. Okay, so we will need to first get the unit vector. We do the dot product, and then remember that's going to be a scalar. we multiply that by the unit vector, okay? And that gives us the component that's parallel to the force vector that's parallel, okay? And then once we have that, we take the parallel, we could take that vector and subtract it from the original vector. So the parallel vector subtracted from the original vector, that's the perpendicular vector. Okay. Then when we got to remember, when we go back to doing work, we use the original vector, not the unit vector. Okay, so let's see if we can put all that together. Okay, let's give this one a try. This is my second attempt. I did a stupid little arithmetic error and didn't end up with the right place, so I decided let's start over. Okay, so let's do this carefully. Remember, we're going to take the force vector times the unit vector of the direction we're going. So to get the unit vector, we need its magnitude. We're going to divide this vector by its magnitude. And that will give us the unit vector in that direction. Okay, so the magnitude, this is a 1, and there's a 3. It's going to be the square root of 1 squared plus 3 squared. That is 1 plus 9, which is the square root of 10. Okay, so our unit vector, multiply each, kind of distribute it through, right? So this is going to be 1 over the square root of 10 I plus 3 over the square root of 10. We're dividing everything by the magnitude, j, okay, little vectors. And now we're going to do a dot product, f dot u. That becomes a scalar, a number, and then we multiply it through with scalar multiplication times the unit vector that we just come up with. Okay, so let's do the dot product first. So for the dot product, I'll go ahead and do it right here. Minus 2i minus 6j. So that's that dotted with the unit vector, 1 over square root of 10i plus 3 over square root of 10j. And then all of this, I'll put just so I don't forget it, will be multiplied by the unit vector. Okay, and to get the cross product, remember it's going to be, well, if you forget, just bring that back up. How do we do a dot product? Is this algebraic definition here? The first component, the I components multiplied together plus the j components plus the k components if we have 3. Okay, so that's the dot product. So the I components are negative 2 times 1/10, so that's negative 2 over square root of 10. No, not 1/10, square root of 10, right? And then we take the j components and multiply them, so there's 6 times 3. This is where I made my mistake. I said it was 24. It's 18. And that's all over the square root of 10. J. And now these, oh, wait. No, dot product. There's no I and j's anymore. We just add these together, or, yeah, so they're both negative. We're just adding these two numbers together, and then we're going to do scalar multiplication times the unit vector. So negative 2, negative 18, that's negative 20 over square root of 10. Okay, and then we multiply that by u. And what's u? It's up here. So actually, why don't I make it a little clearer? We'll just write it in component form. So we're multiplying by the unit vector again. So negative 20 times 1 is going to be negative 20. So we come up here, negative 20, square root of 10 times square root of 10, square root of 100, which is 10. And then negative 20 times 3, that's going to be negative 60. And again, over square root of 10 times square root of 10, which is 10. The numbers are looking much better. This reduces. 20 divided by 100 is negative 2i. 60 divided by 10 is 6. And there we go. Simple little error here. Of course, you didn't see that, and I could have just kept quiet, but I want you to know that there's all this parts to it, and a lot of times in mathematics is we get something wrong, and especially when you're first learning it, you think you don't understand vectors. Well, you did all the vector stuff right, but you made an arithmetic error. That's how I was feeling anyway. So let's do the reveal, and yes, indeed, negative 2i minus 6j. Okay. So, and notice that is the same as f, and what the reason is because these vectors are parallel with each other. Now, if you recognize that will always happen when they're parallel. The force vector is the component because it's going in that same direction. And the way you can recognize parallel vectors is notice their difference by a scalar. So you could factor out a negative 2 out of here. Let's see, pointing here. So you could factor a negative 2 out, which would give you get back to the draw mode, which would give you, let's see, maybe I have to do here, negative 2. So factor out a negative 2, you'd have a positive 1, and you'd have a positive 3j, and notice that's the same. So that's why they're parallel vectors. The cool part is once you recognize that these are parallel vectors, and you might not have recognized it till here, remember to get the component that is perpendicular, we just subtract this from here. And so if you subtract a vector from itself, you always get 0, right? You're always going to get 0. And I guess I could show that, but if your parallel part is the same, you subtract these two, you'll get the 0 vector. So I'll let you take a look at that. Okay. But then when we come down to the force done, remember it's just going to be f dot d, the original d, not the unit vector d. Okay, so let's go ahead and write what we need to write here. So f dot d, let's see, what is f? Negative 2i, negative 6j. And the d vector is just I plus 3j. So when we do a dot product, we get negative 2 times 1 plus negative 6 times 3 and that gives us negative 2 plus negative 18, and so that's negative 20, and that should be the amount of work. Wow, we got it. Okay, and again, that work can be negative. It's working in the opposite direction. Okay, so that's negative work. If it was going in the same direction, it would be, then we could have the positive work. So had it been 2i plus 6j, we would end up with positive values there. All right. So again, if you look at the way they explain it, though, they just say, well, these are parallel, so this is it, and this is this. So they didn't show all this. I wanted to show, if you didn't recognize that they were parallel, that you would end up with it, and you would say, oh wait, how did I end up with the same vector? Well, they're parallel. And so one way, as you're going through the test, take a look, is the direction vector parallel to the force vector? If it is, then the force vector is your parallel component. It's because it is parallel, and so it makes it a lot easier. You could have been done with this in just a quick little review, and boom. So now this one, that's why I'm having us do two. This one, they are definitely, you can kind of see they're not parallel, right? This is, you can't factor out a common thing and get 5i minus 3j. You can't. Well, you can factor out a 2 and you get 3i and 5j, but that's not the same thing. So with this one, we're going to go through the same process, and we'll come up with maybe a more substantial answer, and then that's way we can work on this part. Now, if you're okay with this, just fast forward through this part. But if you want to see another example, let's go ahead and do that. So remember, to do these types of problems, we've got to get a unit vector. So we're going to divide by the magnitude of d, which is the length, right? And to get the magnitude, it's a Pythagorean theorem, thinking of this as a x direction and a y direction. We're going to take the square root of a squared plus b squared equals c squared. That's really what's happening here. And remember, it doesn't really matter if they're positive or negative, but we don't want to get too sloppy. And, it is a -3, but when we square, it's going to be positive. So that's going to be 25 plus 9. That's going to give us 34, square root of 34. So we're going to see it might not be as pretty. So we divide everything by square root of 34. And so there's our unit vector right there. Not too bad. We now take a dot product between the force vector and this unit vector. Okay, so let's come back here. We could probably use a space here. F dot, the new unit vector we've got. And then remember, just so that then it becomes times a vector, because we got a scalar, we want to end up with a vector. Okay, so the dot product part is 6 times, so the I components multiplied together, 6 times 5 over square root of 34 plus 10 times -3. I guess I'll write it out just in case, because what it happens is if you write everything out, if you make, hopefully if, but then you're able to go back and say, oh shoot, I took 10 times 3 and I put 20 or something, You'll be able to find your errors. That's where it becomes important. So this becomes 30, not 36, see? And that's my problem, is a lot of times I will, I said 30, but I wrote down 36. So that's one of the reasons why I write everything down. Yeah, we'll go change colors on us, right? Over square root of 34. And then that's plus, actually it's going to be minus, right? It'll be minus 30. Whoa, what's going on here? Square root of 34. I think we might have another one of these. Well, what's that? That's 0. Whoa, that's kind of cool. What this means is that these must be perpendicular vectors. And maybe I would have seen that somehow. I don't know how I would have seen this. Times the unit vector. Well, when you take 0 times a vector, you get the 0 vector. Okay, that makes it easy. As long as I did everything right. Yeah, that's 30, and that's -30. So the description here, wow, 0. Actually, not 0 vector even, because there is a 0 vector, but all of those are zeros. Well, let's come back here. Sorry. Go back to our drawing. Yeah, sometimes when there we go, just equals 0. Okay, well, what does that mean? So it means that since it is perpendicular, it means, so if we end up with 0 for the parallel component, then the vector itself is going to be the perpendicular component. So I keep going to the wrong screen. So this has to be the perpendicular 6i plus 10j. And yes, when we come over here, here it is. So they give us a couple of these. And again, if you would have recognized that it was perpendicular, this probably has something to do with these changing, but I would just go ahead and do the dot product and say, well, when I get the dot product is equal to 0, that's what it means. We've got that definition in our notes, that the dot product, if the dot product is 0, then they're perpendicular. So then we have this. Now, we come down here, we still do the dot product of the force vector times this. There could be some work done. Now, you might be thinking, well, how, if there's work is going off perpendicular, how could you do any work in this direction? Probably not possible, but let's just do it. Let's see if so we're going to do a dot product between these two, 6i plus 10j. And so dot product with, what was that? That was 5 and 3, I think. Yeah, 5 and negative 3. And yeah, you're going to see we're going to get 5i and negative 3. We're going to get 0 work being done, because then we get 5 times 6 is 30, and then 10 plus, I guess, 10 times negative 3, negative 30. That's 0. We can't do any work because the work is going in the, again, perpendicular to our displacement. So no work gets done. So let's take a look at this one. Then we'll look at one more, and then we'll have the class time to look through the rest of the questions that you may have. So this one, we've got 2 forces working. So one force is pushing an object 50 degrees south at 50 newtons. This is direction north of west, okay, with 120 newtons. So what we need here is to set up resolving these into the y component and the x and y component. Remembering it's the magnitude cosine of the angle is the x component, or the I component, and for the j component it's going to be the magnitude times the sine of the angle. So we got to figure out the angle and the directions, those kind of things, and then finally, when we're all done with this, to get our answer, they want the magnitude. So we'll get the vectors, we'll resolve them, and then we'll get that magnitude. That'll be one answer. And then they want the angle, so we can get the angle with this tangent of theta is equal to this. So the arc tangent is the y component over the x component. Okay, so let's see how this works. So first of all, we set up a little, let's see over here. So first of all, we're going to set up a xy coordinate system. Okay, so let's put the object, and we'll do the vectors from 0. We could do them anywhere, but let's not try to. Let's just draw them from here. Pushing an object in direction 50 degrees south of east, and we'll call this, north. This is east. This is west, and this is south. 50 degrees south of east. So here's east. It's coming down 50 degrees. So this here is our 50 degrees. And it's got a magnitude of 50. Okay, so we can set up that vector, but A second force is simultaneously pushing an object in a direction 70 degrees north of west. So it's going north of west, 70 degrees from west going towards the north. So this is going to be a vector like that, and that's going to be a 70 degree. Okay, so we got that. And we need a vector that will keep this stationary. Okay, so that basically the amount of force worked on it will be 0, keeping it in place. So let's set up this first vector of the 50. Okay, so that vector is going to be, let's call that force 1, because this is the third force, right? So the first vector, using our formula, is going to be the magnitude times the cosine of the angle, and we're talking 50. The cosine is positive, so cosine of 50 degrees. The sine part, though, notice it's in the fourth quadrant. The y component is going to be negative. So we'll put our minus 50 sine 50 degrees. And again, I should put this is a j component and this is a I component. The force 2, we'll notice the cosine component, the x component is over here in the negative region. Right? Maybe we'll label these plus that way. And it's this way. So the cosine is going to be negative, and it's 120 magnitude times the cosine of 70 degrees I. And the y component is positive. It's going in the positive direction, so that will be a plus 120 sine of 50 degrees j. That's really, I don't know if it's the hardest part, but it's the most important part. You got to get it set up correctly, right? So now that we've got them set up correctly, we want the third force, which must be applied that to make it counterbalance the first two. So to make the resulting force 0. So if we add these three forces together, force 1 plus force 2 plus force 3, we have to be equal to 0. Well, so what is force 3? Well, force 3 would have to be equal, bring these over, minus force 1 minus force 2. Okay, subtract those over. Yeah, so that'll give us what the force vector is, right? These are all vectors. And then from there, once we've got the force vector, we'll break it up. We'll find its magnitude, and then we'll also be able to find its direction. They're already telling us the direction. It's got to be south of east, right? Which kind of makes sense. If you got a bigger force pulling it to the west of north, you got to have something counterbalancing this. So it's going to be working with this, not necessarily at 50 degrees, but we'll see. We'll see. Okay, so we use this, and it's just a simple vector addition, but with these numbers. Now, at this point, I would suggest let's turn this 50 cosine of 50 degrees into resolve it into a number using our calculator. Okay, so let's how are we going to do this? We're going to pull up our calculator, put it over there, and then we'll put this back up. Okay, so let's resolve vector 1. Again, we want to come here to mode, just make sure you're in degree. Mine keeps going back to radians. Usually on a handheld, once you get it into degree, it'll stay in degree. But make sure you're in degree mode if you're working with degrees, which we are. And so we're going to take 50 cosine of 50. 50 times cosine of 50. Oops, 50. So that's going to be, now when you do this, since we want to round it, let's see, what do they say? Round your answers to 2 decimal places. My suggestion is to use at least 3, and since we're just adding, I think we're okay with just 3 decimal places, so we do the proper rounding. Okay, so we'll look at force 1 as 32.139, and then we take that 50 times sine of 50. So we'll get a positive answer, but that's why we had to set up the subtraction right here. So this is going to be 38.302. And then let's go ahead and get our second. So 120 cosine of 70 times cosine 70. So that force 2, and again, it starts making more sense here as we see this is minus 41.042i. And in the j component, we have 120 times the sine of 50. And that's a positive, so that's a plus 91.925j. And my j's and my i's don't hook in the right direction. This was my biggest frustration, i's and j's. They're kind of similar, but one hooks to the right and one hooks to the left, and dyslexic people have real problems with those kind of things. Okay, so now, again, just looking here, we're going to take minus F1 minus F2. So remember, we do it sort of component by component. So F3, I'm just going to kind of jump to this. We're going to take negative this plus negative this. Okay, I'll write it down. So F1, so we get minus 32.139. Because it's the opposite, minus a minus, that's going to be a plus 41.042. That's going to be the j or the I component. So we'll do that, and then I'll just put a plus here. I don't know if it's plus or minus, but we'll figure it out. So minus F1, so this is minus, so it becomes plus. Actually, we're going to see it's going to end up being negative. Because it's going to the southeast, that makes sense. The y component would be negative, the x will be positive, so that helps. And then minus this one, so minus a plus, it gives us a minus 91.925, and that's our j component. Okay, so we've got pretty much everything we need here, so I'm going to keep on scrolling up, give us some working room here. So that's what F3 is. So let's actually do the arithmetic. Now this answer is not what we're going to report, right? Because we're going to report the magnitude. What am I looking for? Calculator. I could do the addition in my head, I guess, but it's just let's go ahead and do it this way. So minus 32.139. Right, so I'm doing this part here, plus 41.042. It's got a component of 8.903 in the I direction. I could go ahead and change that to negative. I know it's going to be negative, but let's just do it first. 38.302 subtract 91.925. Okay, so that's going to be, yes, exactly 53.623 in the J component. Now, if they just wanted the vector, that'd be great, because that's all we need. Why did it jump all the way up there? Come on back. Oh, didn't jump that far. Okay, so those are the vectors we have. Remember, we need its magnitude. So magnitude is a squared plus b squared equals c squared, Pythagorean theorem. The magnitude of f3 is going to be the square root of 8.903 squared plus 53.623 squared. Pull up our trusty calculator to handle that one. Okay, let's go ahead and clear all this stuff out. So we want the square root of 8.903 squared plus 53.623. Now, no, yeah, it should be minus, I guess, 53. But in the end, I would just make me put my parentheses around. I just know this, when I square it, is going to be a positive answer. So I took off the negative. So we square both of these, we add them together, we take its square root, and that gives us that its magnitude is 54.357, so 36. Right, rounding to 2 decimal places. Let's see if we're correct. I can't remember. It's been a while since I did this one. Whoa, we're not. Where did I go wrong? Okay, got my sanity back. I know why I'm wrong now. You probably spotted this. Why do you do sine of 50, right? So we come back here. This number here is incorrect. This should be sine of 70 degrees. And I was going to redo this. Oh, let me just do it all. But I want you to see, even when you have the right processes in place, that you could easily, will it let me, I want it, you can easily, let's do it this way. Let's go with the draw. And actually, this is the way you should do. You shouldn't really get rid of your work. You should just come back and say, okay, let's correct it. That's 70 degrees. And when you do that, I took a little break, you get 112, not 91. Okay, so this component here is 112.763. That makes this 112.763, which makes this something different. Let's do that. So it's 38.302 minus 112.763. 74. Different answer. So, and again, I I never corrected this. This is not, sorry, never corrected this. It should not be plus, it should be minus 74.461. And so with that in mind, let's see if we can now match this. Actually, it ends up being close to that, right? So we come in, we're going to correct this. We're going to make this 74.461 squared. And let's see how that works. So square root, let's clear that. Square root is this one. Square root 8.903 squared, and then plus, and again, I know this number is negative, but when you square it, it'll become, the result's positive. So we'll just leave that negative off. It makes the entry a little bit easier, right? And we take that square root. Hopefully it worked. It did. And I didn't check in advance, but no, we don't get that. We get 74.99, rounded to 2 decimal places. Now we check. So notice when you go through these, just this is the advantage of writing down all your work. It's not to show me. It's not to show somebody else. It's so you can see where there's potentially any errors. You've got to find some way to go through that. And when you don't, it makes it a lot harder to go back. I would have really had to start over, and I wouldn't have known where I was at. But if I went here, I said, wait, that's not 50, that's 70, because I could see these are supposed to match. Okay, but we're not done yet. Now we need to find the direction. We need to, so this is our x component, this is our y component. And remember from here, the tangent is the y component divided by the x component. So it's the arctangent of the y component divided by the x component. I mean, is that a z component? No, it's an x component. Okay, sometimes it's hard to see. Okay, so here's the x, here's the y, and so we're going to do arctan of minus 74.461 over 8.903. Hopefully we'll match what they got here. It's going, and since it's going to the southwest, we should have our, now let's see what, yeah, we'll just do it. We might, remember with arctan, it's only good between, I guess I forget my domain from 0 to pi. So we might, we'll see. We'll just give it a try. Let's see, tangent, we want the inverse tangent, our arctangent. And let's try this, 74, actually negative 74. I think we would get the same thing, it's just the direction. We would notice how we kind of deal with the positives. I'm having this feeling like we might get we might not get the right answer. We might get the one we don't want. Well, negative 83. So it's negative 83. That would be an angle from 0 going down. So I think that was right. That was the right way to do it, to think of it. And I think we didn't put that on, we'd get a positive 83 degrees. Yeah, maybe it goes from negative pi over 2 to pi over 2. Sometimes forget my trig, right? So this is saying it should be 83.18 degrees, and the negative is indicating, yeah, that it's going, because we should certainly see it's southeast, so that one of the components is negative, and it's definitely the y component's negative. That's what that's telling us, and the x component. So to put it in this form, we've got its magnitude, and let's just check it. Is it really 83? It's 83.18. So that feels, oops, we'll leave that alone. Leave that alone. Well, there we go. I want to move. No, not that. Leave that there. Anyway, we've got our answers. They match. These can take some time to work through. So, but now you see. Okay. We got one more. Again, this is one from Chapter 12. There's a couple others. We'll look at those during class tomorrow, but I just want to give at least one linear, three-dimensional linear equation. Now, to find this equation, this is where we use, let me get it myself out of the way here. We use this part that we're going to use as the linear equation, z equals this. Okay. So, well, let's see, where's that? That's the point slope. So once we have the slope, we can use the point slope. Okay, I'll show you how my approach is going to be a little different than what the approach of the text is. The text is we've got 3 points. Let's get 3 equations and find out the unknowns. But I'm going to use this form here, this sort of point slope formula. Okay, so z equals z naught plus this. Okay, so z equals z naught plus m x minus x naught x1 or x naught, with probably x naught, which we're going to call x1, or let's see. Yeah, they're all so we'll choose whatever point we're going to choose as x naught. Okay, x naught plus n, which is the slope in sort of the y direction. The change of y over the change of z, right? Change of z over the change of y, change of z over the change of x. Okay, that's what that is. Okay, so to get m, we want the slope. This is going to be the change of z over the change of x. So what we need is we need a point where the y coordinates are the same, and that's, so we're going to use this one and this one, because notice the y coordinates are the same. So what's happening to the x is we're getting 3 minus 1, right? 3 minus 0. Sorry, 3 minus 0. What's happening to the z? We get 0 minus 1. So that gives us a slope of negative 1/3. That's our m. For our n, we need a point where the x coordinates, let's change colors, where the x coordinates are the same. So here the x coordinates are both 0, so now we can talk simply how z changes with respect to y when x is not changing. Okay, so this is a change of z over the change of y. And let's see, so what we're using these 2 points. So that's the y is 8 minus 0. So 8 going from 8 to 0. How is the z? It's going from 0 to 1. So we get a minus 1/8 as our slope. Okay, so that's n. So we can plug these in, and then what this x naught, y naught, and z naught are, well, those are the values from one of the points. We could choose any of these. The one that looks best to me is these 2, because x is 0, y is 0, so those are just going to sort of disappear, and then we've got a 1 here for z. We would end up with the same value, or we should at least, if we put any of these points in And you could check me on that. But so what we're going to do is we're going to get z using point slope form. Z naught from here is 1 plus negative 1/3. That's the m times x minus x naught. So x, well, let's just do that. X minus 0. Let's do it that way. I put 1/2. It's 1/3. Okay, pay attention. Little girl, that's me. Okay, and then I got my slope in negative 1/8. And that's going to be y minus y1, which is 0. So that's kind of cool. And so yeah, we get z equals 1 minus 1/3 x times 0 is 0 minus 1/8 y. That's our formula. Notice z equals, hopefully it's what we got. Hey, looks pretty good. It's what we ended up with. So that's how you can find the equation of a line when you've got 3 dimensions, the linear function from 3-dimensional stuff going on. All right, so that's all I've got for our review so far. Please come to class. Hopefully you've worked through some of the problems. We'll answer more questions. And then on Friday, we'll have an exam that will deal with all of these things. Thanks.